So, oh, someone is already here. Good. Just a gentle reminder for the mean first would be your tutorial and assignment, right? So make sure that you know your the tutorial will be next week, and then you'll be the assignment 2 will be due on next Tuesday. Okay, make sure that you submit because you submit, you get the grade. If you don't submit, then we don't accept late submission. Just make sure you know. Now, I think we are just slightly behind the schedule. We covered the consumer, producer, and equilibrium already. So what's left, the basic before we go to second part of the course, game theory. So before we do that, we talk about how to handle uncertainty or probability. It's a big chapter, but I think we should be able to finish almost all of them, but probably not 85 slides, but at least majority of them can be done. And for sure that this is a huge topic. I mean, if you go to many graduate program, actually this would already a whole semester course. So I can just touch a very barely the minimal, and assuming you don't have any knowledge, we start from scratch because we can't really assume you know anything there. So I would try to say what is in the frontier in this research, but we really can't go too deep anyway because of the time constraint. So uncertainty, probably you would ask, so far we consider equilibrium, we consider competition, and then why we don't take care into the uncertainty. And indeed, economists don't understand too much uncertainty until very late. You look at Adam Smith, I mean, of course they know it, but they didn't know how to model it, right? And then in particular, right, when the lemons market I mentioned last time is the thing that comes out, and then people, I mean, economists try to see actually information will be crucial, right? Because before they would think information with just a minor change to the outcome, right? Maybe less efficient, and that will be the case, right? Just like you can imagine, right? And in the physics, right? Newton actually invent laws of motion, and then friction will be just part of the game, but doesn't change things a lot, right? And then you would care about things that in normal days, right, then Newton mechanics would work, but when you go to, right, high mass, high energy, right, then you have to consider the case, right, quantum mechanics or Einstein relativity idea, right? Same idea here, right? When things get important, uncertainty get serious, or when the future is not so clear, then you can't avoid it, right? And then we also have been avoiding is interaction, except Conrad, Bertrand, right? So that will be the key of the second half semester when we talk about interaction. But here we touch some idea on uncertainty because we need them to do game theory as well. So how to model uncertainty and risk. And in the literature, there's a actually they distinguish them in two ways. One is called risk, one is called uncertainty, and risk would be just imagine the standard case, the gambling, you know, actual probability of things, okay? Or we kind of like we have good idea what's going on. And uncertainty, there's no objective probability, right? Just you roll a die, then yes, right? You know if the die is fair or unfair from the data, right? Can be repeat and things if you really can't say, right? And actually, I would say most of the case in our life is facing a lot of time is uncertainty rather than risk, right? But risk is much easier to handle, so you can look at all the textbooks, they focus on risk. That's what we do. Uncertainty, at the very last few slides, I talk about them. So we require much more difficult because you don't have objective probability. Okay, there was some way to model it, but I think in business application, in most of them, we focus on risk rather than uncertainty. But in many cases, people don't distinguish them, okay, when we write model. But if you go to this literature, this field, they would distinguish between the two. And again, there are too many ways to model risk. There are so many models because, as we said, right, there's only one way to model certainty, but there are many ways to model uncertainty, right? Or there's only one way to model rationality, right? But there's so many ways to model irrationality. Okay, so you focus on simple case, right? It's the way that you learn in probability, the classical probability in your undergrad, right, or even your high school, right? It's a risk situation, right, where you know the list of outcome that is possible, right, but you also know the probability of each outcome, right, and that is a big assumption there, right? It only applies to casino, maybe, right? But when you look at magic show, that is not this case, right? For the magic show, you actually bring surprise, right? When the magician put the hand in the head, right? You don't expect a rabbit comes out. Maybe you expect, but it's usually other than rabbit, right? Something big comes out, right? That thing comes out that is you don't really expect, right? You have to know the probability, right? You have to know each possibility there. So that is something that a big assumption, but we use it all the time anyway, right? So the next we start with the simple cases called gamble, which similar to what you learn in the probability class. You have n outcomes, 1 up to n is finite, and it turns out that when n is infinity, then things become very complicated. And those of you who do account finance, then probably will worry about the infinity thing. Yes, infinity thing that actually has to be carefully taken care of. In some most of the theorem would hold, but in some of the theorem you require stronger assumption for continuous thing to hold. But usually that's not a big problem, but you have a stronger assumption. But is this stronger assumption hold in your model? That's the issue. Okay, it's always not a problem, but we'll just live with the standard model. We have n outcome, and each one probability becomes 0 to 1 and sum up to 1, right? That is standard idea. And we have a simple gamble will be written as P1 circle A1, right? Pn circle An. This is the way that right gamble, which means that A1 probably P1 and An probably Pn. So this is a notation used in the textbook by Perry and Rennie. Okay, and you will say this 0.5 circle 1, 0.5 circle -1 means the lottery will give you $1 with half probability, and -$1 with probably 1/2. So there's nothing new there. I think the more common is this one, which is compound gamble. Is the way that you describe the world. You can imagine this actually a decision probability tree, right? Because let me draw that here, right? Let me finish the description before we go. So here is instead of a gamble, but you have a second order gamble. You gamble over gamble. That's called compound gamble. It's combined together. So you would be lottery probability alpha over G1, right? So, and then once the nature decide gamble one is being played, right? And then they would draw probability there. So let me write a probability tree. That is the way usually people represent, right? It doesn't work the pen, but simple gamble is like this, right? We have A1, A2, up to AN, right? And P1, P2. So this is simple gamble, okay? And compound gamble is like this, right? You have alpha 1, alpha 2, alpha n, right? And you have G1, G2, Gn, right? And G1 can be corresponding to A1, A2, up to AN, right? So the nature would first choose which gamble to play and then over it, right? Of course, it need not stop at 2-layer. You can gamble over gamble over gamble over gamble, right? So potentially, this kind of idea a tree idea can cover everything we want to have. Okay, that is the classical way how economists think about the world, right? Something happened, right? You can only forget about the inner working, just focus on the end. So the simple gamble is the way we're going to work. And later you will see, we assume the individual only care about the outcome, but not how the outcome arises. So we just look at the last or the end note rather than how we achieve there. So basically what we will do is we will reduce the compound gamble to simple gamble, right? Then by doing so, we don't care about the shape of the tree arise, okay? So, and we don't really care about which actually you get a outcome 1 from gamble 1 or outcome 2 from outcome 1 from gamble 2. As long as outcome is the 1, then it doesn't really matter, right? So that would be the idea. You don't really care about how you achieve. You don't care about the process. Rather, you care about the end outcome only. Okay, and whether it fit or not. Okay, there's a lot of cases that turn out to be very important, the process rather than end outcome. But in our discussion, we only focus on end outcome. Okay, and there are models that tells you that the process is also very important. Okay, there are models for that, but a classic model, which you will know already, expected utility model, only focus on the end outcome. But that would be, we will be going slowly on that. Okay, so that would be, the example would be, say, if we have you have 2 cases, you toss a coin and roll a die, right? If half of time you roll a coin, half of time you roll a die, right? But if you get to gamble 1, you are winning. You get to gamble 2, you're losing, right? So basically, toss a coin, decide whether you are winning or losing, and the amount of win you lose depend on the face value of the 4-sided die, right? It's a equal probability, one quarter for each of outcome. Okay, so basically, toss a coin, decide you win, you lose, and once you decide you win, you lose, you toss a coin. Sorry, you roll a die. Okay, and that is the compound gamble, right? So if you don't care about this, you may only care about the outcome, then you don't care about the amount, right? You don't care about how, at the end, how much you have, right? You don't really care about how you get there, right? So that if that would hold, that would be, later you will see this is our assumption there. So outcomes, okay? And as I said at the very beginning, we focus on finite number of outcomes, and you should check the textbook or thing. They'll tell you that when you go to infinity, things become more complicated, okay? And why we care about only outcome, later you will see, because we only focus on simple lottery, okay? So here we have a simple lottery, will be just 1 up to n, okay? And because we fix the outcomes, so just basically we can represent just the vector of the probability, okay? And this probability must add to 1, so that's why it's n-1 simplex. So that is the notation that in the math we say, right? The simplex is the list of number that is non-negative but add to 1, right? And here of compound lottery, right, will be represented by alphas, which also sum to 1, and also bunch of p's, right? And that would be the idea, okay? So just go back to the slide here, right? Just why you can do that is because suppose you may imagine, right? G2 and G1, the outcome may not be the same, right? But it doesn't really matter, right? We just reorder them, right? Because the n is finite, right? Because you may imagine, right, they are not the same outcome. Then you can just call it a n plus 1, a n plus 2, so on and so forth until the end, right? So if every outcome is finite, you can just list them. If they're the same, you can give the same name. You give different name. If they're different outcome, they give a different name. So there's no loss of generality to focus on a fixed number of outcome. Okay. And this is the example, right? So you have 6 outcomes. You just list the probability vector or the element of the simplex in n-1. Then 1/6, then you're done, right? Or you can tell me the vector of k dimension and then tell me the probability of each k possible lottery you're going to draw, all right? Half of time you have the P1, half of time you have P2, so that would be the idea. Is that okay? So instead of outcome, we just focus on probability because that would simplify our notation because the outcome has been fixed already, okay? So that is the notation. So let's quickly jump to the real stuff, okay? Is that okay so far? Just basically, we are focusing on finite outcome, okay? And then we can describe the world by simple lottery, compound lottery. Simple lottery is just a list of probability because outcome are fixed already. And compound lottery will be, I will have, say, suppose I compound over k possible lottery, right? I will give probability for each one of the k outcome that comes, this alphas, and each lottery will have n possible outcome, right? Now, we will try to give you, I guess, probably one of the first model to describe how individual decides when they look at risk situation, and that is called the expected utility. And I guess this is still the model that we're using, right? And you can imagine this is possibly the rational model, right? Suppose you're the AI, you're the machine, you want to make a decision, this is what you should have done. So this is a normative model as well, right? So if you want perfect rationality, you want the model work very nicely, and then this is the way thing you should adopt, right? And if you think about an institution, how she should behave, then it should be follow expected utility. But if you want to model real human, then possibly this is only a good approximation in many cases. Okay? And because human are a lot of, especially when it comes to uncertainty, we don't really do it very well, right? Imagine yourself, the simplest case of chess or Go or other simple game, right? We know how to solve it, right? But we don't play very well, right? If we are perfect rational, there's no point of playing chess because we all do the draw all the time, right? Because of we have some rationality issue there, then we don't, right? But anyway, let's look at the expected utility framework, which gives you the very basic model. And so as we said, we all fixed a set of outcomes to n outcomes, and you have simple lottery there, okay? And so we have to assume because simple lottery is so simple enough, so we make the assumption that the individual is able to form a preference relation over simple lottery. We don't say the agent able to say a lot of things about compound lottery. We only assume this agent is able to say, give you n outcome, I give you probability, okay, over n outcomes. In one situation and the other, he must be able to say, okay, one is over the other over another one, or both, okay? So he must be able to say which one's better. He can't say, I can't decide. He can say that they're similar, but they can't say, they can't decide, it depends on other things, right? So that's complete. And that has to be consistent, right? If P bigger than Q, Q bigger than R, and P bigger than R. So if you come from topic 1, shouldn't be that big issue here, okay? And looks like this is kind of okay, but turn out that in experiment or in many cases, completeness usually is not an issue, but transitivity often is a big issue there when actually people try to ask them to make decision. Transitivity turn out to be, a lot of them, they're violated. And of course, completeness shouldn't be a big issue, but of course, it's very difficult to test completeness in experiment, right? Because you have to be able to give all the lottery, and then they have to say yes to all, right? It's easy to negate it, right? But it's not easy to see how they hold. But in general, it's okay to assume completeness, but transitivity can be an issue there, especially when the calculation is very complicated. people can easily overlook. So because of completeness and transitivity, okay, and then we can write the indifferent if both of them are true. And also we can compare, because completeness, right? We can compare the case of the corner case, where each outcome comes with certainty, which is one seal A1 and all of them are 0, right? And one circle AN, right? All of them are 0, right? I can compare the case where things come out with certainty, right? Because of completeness, okay? And because of the completeness and transitivity, we can assume we can rank from the best outcome to the worst outcome, right? That is by construction, okay? And turn out that you will see this is very crucial for the proof. The existence of the best outcome and the worst outcomes is crucial. That's why we will say when you go to infinity, this part can be, the proof doesn't work, for the current proof doesn't work for infinity. You need some other thing for it to work, okay? So the simplified notation, once circle AI is just AI, okay? We just abuse notation, okay? Now, with this, we will have invokes what we call continuity, which we know already. The one we'll use is 2 when we talk about the preference when we have certain case, right? When we say a bundle X is slightly better than Y, we say slightly change in X will be still slightly better than slightly change in Y, right? So the same idea here. If lottery P is better than Q, you can always find something nearby P and nearby Q such that this preference continue to hold, okay? And this is good, but we also want this is actually equivalent to the above, okay? Which we have used it, but you may not be aware of it. When we continuity, we say when Q is somewhere in the middle, right? You have P, Q, R, Q is somewhere in the middle. You can always find a mixture of P and R that is same as Q. So that means that I have a high bundle, a low bundle, and middle bundle. High better than middle and better than low, right? And I can always figure out how to mix the high bundle and low bundle such that you are indifferent between the mix and the middle. Okay, that's continuity. If it doesn't exist, actually there's some jump, right? So there must be some way that you can mix and match equivalent to the Q. Actually, the same when you talk about the case in the topic 1, but we didn't write it down, but they're equivalent, right? You can imagine there's bundle X and bundle Y, and C is the middle, right? There's some way you can mix the high and the low bundle should be same as the middle bundle, right? That is the continuity. Otherwise, Y doesn't hold because in other cases it's not continuous, then there's certain jump, right? So that would be the idea, right? That say always you can find somewhere in the middle. And this is also the crucial in the proof, which we will try to do the proof because I think it's instructive to do the existence of equilibrium proof. So the next one, I think that is rather trivial. I think you would agree as well. So I have 2 outcomes, I and J and I better than J, okay? And you have 2 probability, alpha and beta. Alpha is bigger than beta, okay? So your better outcome. So you have 2 outcomes, I better than J, and you have 2 probability, alpha bigger than beta. If you have more probability on better outcome, okay, alpha is higher than beta, okay? If higher probability on the better outcome and lower probability on a worse outcome, you would prefer the left-hand side to the right-hand side, right? Left-hand side is higher probability at a better outcome, right? You have 2 outcomes, right? You increase, suppose they're the same probability, put it this way, right? Suppose they are equally likely, okay? Then your same doesn't really matter, right? And suppose you increase the probability of the better outcome, Of course, the apt one, then you must reduce the probability of worse outcome, right? And you must be better off, right? If you keep doing so, actually you keep improving your attractiveness, right? More likely to get a better outcome, right? So at the end, right, you would have this, right? You start from the same, right? The two outcomes are the same, right? You increase the probability of better outcome, or you reduce the probability of worse outcome. Then you must follow this, right? So that is monotone, right? So you are not crazy. So it's kind of very natural. I don't see in any case you will violate this one. And the last two, of course, the last two is pretty strong, I would say. Okay? But it's also rational if you imagine that this is the way you make the decision, right? If P is better than R, okay, and that is for sure you like that, and I add a common element Q, it shouldn't change. Okay, so P is better than R. Okay, but now I do a compound lottery. I have alpha, I have P, alpha times R, and 1 minus alpha, I got a Q. Okay, so that means that if I did that, right, they're the same, right? If P is better than R, okay, it's a simple lottery. I consider the compound lottery, right, where I have alpha of time, I get what I P and R, but the same element if I didn't get it, right? So that would be how simple lottery with the compound lottery. Okay? Again, you can reduce the compound lottery to simple lottery. The common element there can take it away. Okay, basically this axiom is trying to doing what? You have axiom on simple lottery, right? You need somehow extend the compound lottery, right? The easiest thing to think is, okay, the common element there, I just take it out, right? I just replace it, become a simple lottery, right? A common lottery, they have common component, then I take it away, right? Or a simple lottery, I can build a compound lottery there. Okay, so that's the idea. Now the other one is even more stronger, right? In the sense that if I have a lottery, right, over K, right, that is same as, okay, I only care about the simple lottery. Okay, I just look at, because each lottery have n outcome, right? Remember, this is P1 is a list of probability for n outcome there, right? So this is lottery over K lottery. And this is only one lottery. And each lottery will, let me write that down. Make it easy, otherwise you don't know what I'm saying. So this is the last one is saying the following. Okay. It's following. Let me write down here. So it means the following. So we have alpha 1, alpha 2, alpha K. Okay. Remember, each one will have n outcome. Okay. And each one you have n outcome there. Okay. And I make n large enough so each one you describe it the same. A1 here the same as A1 there. A1, AN, right? And this is P, I don't notation. It's P11, that should be P0. P11 there. This is P1N. This is P21, right? This is P2N, right? This is PK1. This is PKN. Okay? This is equivalent to the following simple lottery. There's A1 of the AN. But how likely get A1? A1 will be just all the first branch there. Will be alpha 1, P11, right? So it will be the probability of this guy is just alpha 1, P11 plus alpha 2 P21 plus alpha K PK1, right? And go to the N one will be alpha 1 P1N, right? Da, 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 alpha K PKN, right? So this is how each outcome, right? And if you rewrite this, it's just simply you just add them together, right? Just a vector. So basically just they are equivalent. You don't care about how you get to the outcome, you just care about the probability. So it's a reduction. Basically, you're reducing the compound lottery to simple lottery, or I can expand, they're the same. Okay. Why we did that? Because we only make assumption on individual how they make decision on the simple lottery, right? And how to solve the complicated model is by assumption that they are able to think, okay, I don't care about how the outcome comes in. I don't care about which lottery comes in. I don't care about the result, right? It's not the process, but the result, right? So that is the idea. Now, once you have that, for example, like this, right? You have two outcomes. Lottery, you have two probability. You consider compound lottery, right? So that means that, as I said, right, you would have add together, then this is how you get a number there. Okay? You can check, right? That's equivalent to this, and if you have reduction, you are indifferent between this and this outcome. Okay, either have outcome one have this probability, outcome two probability, or you play 0.3% lottery one, 0.7% lottery two. Okay, you don't distinguish the two. Is that okay? So now we are ready to prove the result. Okay, and I don't prove this statement. This is relatively easy. You can check. We will save our time to do the most important proof. It's saying that independence is pretty strong, and independence implies monotonicity. Okay, the proof is just 3 lines, but I'm not going to prove it. So basically, we assume independence, and that means that we have the monotonicity already. Okay. Okay. So the proof is like this, but I don't want to bother you with the proof because it's just 2 pages of proof. But what I want is to show this Neumann-Morgenstern theorem, okay, which said the following. Suppose the individual have 5 axioms we said: completeness, transitivity, continuity, independence. Remember, independence implies monotonicity already, and reduction. And it turned out that the agent preference, okay, can be written as just expected value of the utility. Okay, you don't need to care about how they look at the lottery. You need to look at how they look at each outcome. Okay, it's utility of a lottery. It just look at each outcome, utility of each outcome, right? Which outcome is actually, remember, this is one circle A, right? Look at certain outcome. Okay, look at how they look at the outcome in a certainty case, and then weighted by the probability. Then you're done. So this is an amazing result because you don't need to worry about the structure of the lottery even. You only care about the preference over certain outcome. Okay, and probability actually plays no role other than weighting, right? And you can see this is a very strong result, right? You may be expecting this would affect the outcome in some way, non-linearly, right? Because the probability change doesn't change your preference linearly, right? Sorry, only changing linearly, right? There's no nonlinear outcome. There's no interaction. Okay, there's nothing there. So it's very simple, right? It doesn't have to say how A1 related to A2, A3, A4 have nothing to do with that, right? So that is of course, because those so amazing simple result, that's why every people use it, right? That's not nothing is not very complicated, right? Because it's very abstract, right? It doesn't say anything about the A's, right? And you only depend on certain outcome. So we'll prove this one, and then we go to the break. So we actually try to prove this one. I think that is worth spend some time on it, because I guess our class will at least have two proofs that we go over. One is prove the existence of utility, and then we'll go to a more difficult one, existence of expected utility. I think these two should be, you know, how they were proved. Okay. So the proof is turned out to be not too much different from what we have. It's just like, just go overview. It's just like 3 slides proof. So it's not something like super complicated. So that's why I think we can use it. So since the outcome are fixed, I use lottery and gamble the same. Okay. And first, this is trivial case, very trivial. Okay. It's saying that all outcomes are the same. Okay. A1 of the AN the same. Okay. By construction, that is very simple. If everything is the same, every lottery is the same, right? Because you start from everything the same. You have the independence, you can build up any lottery, you're indifferent. And in that case, you set everything to 0, then it's fine, because everything is the same, right? So we're done, right? Because if everything is the same, every outcome is the same, then it must be every lottery the same to you by the reduction or independence argument, right? By independence argument the same, right? And we just set this to 0, and any lottery give you the same, right? Then this utility function represent your preference, right? Because everything do the same. So this is trivial, right? There's nothing to study. So this slide is empty. So this, we come to second slide. This is the key slide, but the proof is not complicated, so don't worry. So suppose now we have A1 better than AI for the AN, right? AI must be between A1 and AN, right? Okay. It's the best outcome and the worst outcome. And there's something in the middle. And here is the bias of continuity. And also that's why the finiteness kicks in, right? So there must be the thing. And this is very similar. If you remember how we prove the thing is, we have a number that represent, okay, the lottery over the best and the worst outcome, okay? Is our alpha, and later you will see this alpha is our utility, is our is closely related to our utility. Okay, it's actually utility. Okay, and if you remember how we do the topic 1, actually the same thing. Let me show you the slide. Remember how we did it? Is we go up and go left, and you find a number on the diagonal. If you still remember that proof, how we did that. How we did it, if you still remember. Of course, we also have monotonicity here. We have this bundle and this bundle, right? We go up, slightly better off. Go left, slightly worse off, right? And we must be able, actually by continuity, find something is indifferent to this guy, right? And this number, the forward degree line, is our alpha, right? Alpha turns out to be our utility. Same goes on. But of course, we don't go left and right, right? We know there's many bundle here. There'll be a worse bundle there, the best bundle there. We're able to find the lottery and such that this is equivalent to this. Okay? So that is the idea. Sorry. So alpha is the probability that you are mixing over the best and the worst outcome, right? And this number must be unique. Why? Monotonicity, right? Independence, imply monotonicity, right? Because the one is better than n, right? So increased alpha must be make you better off. So this alpha must be unique. Okay. And that also comes from our monotonicity in the topic 1, right? The same thing. And we just write this is the utility, right? And by construction, okay, we can write the best outcome has utility 1 and the worst outcome is 0, right? because probability, right, between 0 and 1, and then you can always write this way because it's consistent, right? Because A1 is equal to 1 and 0, right? So that's coming from this guy, right? That means that every outcome can be written as this utility times A1 and 1 minus utility times AN, right? This is, just replace this to here, right? This line has, I hope there's no problem. Okay. And that means that we can reduce any outcome to a simple lottery over A1 of AN, right? Because every outcome is just a lottery over A1 AN, right? A1 is just have probably 1 and 0 have N, right? And AN will just probably alpha is equal to 1, right? So that is the same thing. Okay. And by independence, right? Any simple lottery just mixing A1 to AN, right? Doesn't really matter, right? Just that's how you define. Okay. And that means that if you have P, right? It just the probability over A1 to AN, right? It just, you can write in this way. Maybe I write down. This is a little bit complicated. Let me write down in this way. So you can imagine this is P1, A1, right? And P2, A2, right? So this is our simple lottery. Remember why we only care about simple lottery? Because that's the reduction argument, right? So, but remember, any AI can be written as the following: is UAI of A1 minus UAI times AN, right? So this is this assumption, right? Come from the A1 is better than AN, right? And then by continuity, right, you always can write in this way, right? So that means that I can use the reduction argument, replace this to here, right? That means that what we're doing is the following. We're doing is we have P1, okay? And then we have U of A1, which is 1, right? 1 minus U of A1, A1, AN. And similarly, P2 is just A1, AN, U of A2, 1 minus U of A2, right? And so on and so forth until Pn, you replace everything by this two lottery, A1, AN, right? U of AN, 1 minus U of AN. All right, so basically you replace every outcome by lottery over A1, AN, right? Because you can always do the equivalence, right? You can always say the simple lottery is same as this compound lottery. Is that clear? It's clear at this point, okay? But this, remember, you only care about outcomes, right? So you can just look at A1, it's just sum of this probability, and AN just sum of this probability, right? And this is equivalent to the following. Actually, I should have, next time I should have drawn this diagram. The proof is done, right? I should have done that. So it's just A1 and AN, right? This is equivalent to this guy, which is P1 UA1 and PN UAN, right? Because you just collect all the A1s here. And you collect all the AN here will be P1 times 1 minus UA1, right? And so on and so forth, right? So this result, if you write down carefully, it will be just this guy, right? Okay. And once you have this, then we're almost done. Why? Because every lottery is just A1 and AN, right? And that means that if a lottery, this is bigger than this, if this is bigger than this, right? Because we just replace. Okay. But monotonicity implies that you have two outcomes, right? This is better than the worst. If A1, the probability of A1 is higher than this guy, right? And this is better than this one, right? So because they're same, right? One is better than N. You have higher probability of getting a better outcome, then you're done. So this is already our result. So just basically what we're doing is looking at probability times utility of the certainty. So we're done. Okay, that's a proof. Okay, let me repeat the proof because I think let's slightly a magic here with the first time you see it. Okay, the magic is we keep using the independence and reduction all the time. Okay, the first step is to say each outcome is equivalent to a lottery over the best and the worst. Okay, and this probability is actually your utility over that outcome, right? The fixed outcome. The best outcome, you call it 1. The worst outcome, you call 0. Basically, you put a number. The best outcome is 1. The worst outcome is 0. Anything in between, we'll put a number that is the probability that you are either have best and the worst. So that is the utility, turn out to be. Okay, we'll prove it. Okay. So once you write down in this, every certain outcome can be written as lottery over this certain, the best and the worst, right? And because simple lottery is just mixing this certain outcome, right? This is mixing one, right? Then that's why you can say it's equivalent. And lottery is just going for 1 and the N, right? Because that is the graph over here, right? Because right you have any simple lottery replaced by 1 over N, right? And then you reduce that to this again, right? So it's a kind of magic, right? Just step 1, right? We write everything into 1 and N, right? And you collapse again, right? So reduction use 2 times, right? So you just expand your N lottery, N outcome into 2 outcome, compound lottery, right? And then you just reduce the compound lottery back to a simple lottery, right? Once you do that, because this is better than this one, there's 2 outcomes. The only matter is the probability of here, right? You don't really, because they're complement anyway, right? Must be up to 1, right? This better outcome. So only matter is this probability, and this probability is your preference. And that's how it proof being done. Is that okay? So it looks like magic, but this proof I think is worth studying because the structure is very similar to proving existence and utility, right? It's very similar. But here we use another different step here, right? We have a reduction of this. Maybe I should take a picture and next time I should draw it in my slide because I think this is easier than looking at the math because this is the graph, right? It's a graphical representation of the proof. I think this is the better one. Maybe I should next year, if I teach again, I will use this graph only because this is the proof, right? Basically, this is a proof. Okay, so I hope it's good because now you know 2 basic proof in economics. Then you can happily talk to anyone. You know how to do some proof, right? And that is the main thing, right? Because actually, this is very close to what I'm doing these days. Proving existence of certain thing, representation. But you never know when you use it, right? I usually at the beginning I thought this is something just a trick for mathematician. I mean, I never able to use it. And these days actually I'm using this kind of construction a lot when proving stuff. But anyway, so maybe just one final slide. You will see because the way that the number is, right, is linear, right? It's linear. So if you add any constant, have no change in the utility function, right? And you also multiply anything has no change in the utility function, okay? But that's the only thing you can do is offline transformation, right? So it's a cardinal, right? And which means that this is an actual number there, okay? Compared to utility function, you learn topic one. Topic one is ordinal, right? Here's cardinal, okay? And you probably ask why we care about ordinal and cardinal, right? Why we make a big fuss about this, okay? Actually, it's related to in the old days when people are obsessed with measurement. And in classical measurement, you have 4 different type of data, right? You have nominal data, your ordinal data, your interval data, your ratio data. And this is a classical paper actually appear in Science, and all the science will care, right? Ordinal, nominal data is just like the name, right? Gender, right? Ordinal data is the Likert scale 1, 2, 3, 4, 5 when you do the cost evaluation, right? I mean, the difference doesn't make sense, but the larger number is better, right? And you also have the interval data, which is this case cardinal utility, which means that like the temperature, right? Degree Celsius or degree Fahrenheit, difference makes sense, but you can't do division, right? But the last one is the ratio data, right? The zero, there's true zero in the scale, okay? And that's why when you talk about utility, they do care about whether it's ordinal or cardinal, okay? And when cardinal, that means that when you do regression or when you do things, then you can't really do any transformation. Okay? When you do transformation, you estimate, there's a problem, right? Because when you talk about ordinal utility, you can take log or both sides, it doesn't really matter that much, right? The MRS. But when you have cardinal utility, you can't really do those kind of things, and then you take transformation and do regression is another issue. So you can't really do that. But later you will see how we're able to handle this problem after the break. Okay. So let's a break. I think we have covered the foundation for expected utility. And after the break, we talk about a little bit more thing about how to look at the risk preference, how people make decisions under risk. You compare people. And fix a lottery, you compare how people like it or not. And here we will compare different lottery, okay? And we'll do some application, okay? After the second break. So that's a break of 15 minutes. And as I said, we just do you reply in case you want to ask me a question, and just to check out the attendance as well. Time, feel free to fill in. I see 15 minutes. So we'll be 10. Forty-two.我大概一定要去，跟不上，但是我们还是体验一下那个经济数学的一次最后的美丽，这样你还挺美。啊，继续讲。 Là chuyển vào cà phê là sẵn. Rồi em vẫn chỉ có cà phê. So I hope you have a good break. See if any question that I need to answer. Probably okay. That's no problem. Nothing. So the proof that William theorem, I think that's one of the most important result, because without that we can't do anything with uncertainty. So it greatly simplify our life. Yep. So I guess that's fine. I don't want to bother you with this. So let's continue. So what we have done is look at the existence utility, and then after that we look at, based on the expected utility result, we kind of look at different people, okay? How different people react to different lottery, how the utility comes about. And that is fixed lottery. We look at how people behave. And then here we will say compensatory means that we are, can we say which one lottery better than other, regardless of what kind of risk attitude you want. Okay, later you will see. Can we compare without going into detail? Okay, and then we'll talk about some application. So let's quickly do it. So to make our life easier, instead of A1 up to AN, we will have the set of outcome actually a subset of numbers. Okay, and then usually we can represent it by random variable L, continuous random variable, and we have a CDF F and density function F, and then utility can be represented by, expected utility can be represented by this one, right? So this is something you learn from undergrad, right? So the expected value will be just this guy, okay? Do note that there's no U here, right? Just expected value. And if this is gamble is fair, means that the lottery give you 0, right? It's not going to give you anything special. And here, of course, is the old question of the problematic expected utility, right? So expected value, because in the old days, people think that expected value, which is this guy, is same as expected utility. Okay, so that is, and of course, someone come with something that what we call St. Peter paradox, which turned out to be this has expected value infinity, but in practice, no one pay more than $8 for that. But let me describe in detail what it is. This is the game. It's a potentially can go to infinite, and you flip until you get ahead. So the first time you get ahead, you get $2. If the second time, the first time you get a tail, you continue, and then you get ahead, then you get $4. If you get tail head, then $8. If you have tail head, you get 16, so on and so forth. Right? Every time you multiply by 2. And you can easily see that because it's a fair coin. 1/2I is the probability, and 2 to the power I is the payoff. And you each time it's just 1. You add up infinite 1 is infinity. So the question is how much you want to pay for this one. I guess it's final number for you, right? I don't think you want to pay infinite for this, right? It's a final number for that, no matter how big it is, right? So that means that expected utility, so expected value, is not expected utility. And in other words, even it's fair, right? This is fair, right? You don't always want to do it, right? If I ask you to pay infinity for this one, you're not going to pay for it, right? So turn out, as I said, you actually don't pay more than $8. Okay. And how do they solve this problem? Is they think about the utility must be concave, right? Because it's P times U, right? If U is a convex, then it must go to infinity, right? So if U is linear, you go to infinity. If U is convex, also go to infinity. The only possible case is U is concave. So that's why economists start to think about concavity. Okay. So, but in still, we would be talking about, in many cases, we simplify our calculation. That would be true as well is we assume there are agents that only care about, don't care about risk. They only care about the expected payment. So they only look at the expected value of the lottery. Okay. So that is always assumption. Actually, even in finance, you will see that investor, they're risk neutral. Okay, because that things become simple, right? They may be large investor, or large financial firm, or these are all risk neutral because they have very big assets. Or later you see, right? You have a lot of money. Okay, then you pay a small lottery, probably you're risk neutral, right? Suppose you're paying a lottery of, say, paying 1 cent or 10 cents or $1, even $1, right? I think you are okay. Toss a coin, you win, you get $2. You lose, you get 0. You pay $1 for this. Probably you're going to pay, right? You'll be fine. If it's a small amount, then you probably risk neutral. Okay, and that goes for all the many assumptions. That's why the wealth is large enough, and the bet is small. Then you only care about you join is fair. Okay, you have a lot of money. Okay, so that would be it's still, despite the St. Petersburg paradox, it still use a lot of time. So if you look at the expected, okay. And in our model, expected means that it's linear. Okay, there's proof. I'm going to skip it. Okay, it will be like this. Doesn't really matter, right? If average is 1 and 3, same as you just get the 2, right? So you have the 2 cases, either get 2 or fair lottery over 1 and 3. Okay. If you're asking you just get 2, this is your payoff. If you get lottery over 1 and 3, is half of 1 and half of 2. So half 1 and half of 3, same as 2. So only linear will satisfy this constraint. We're not going to prove it, but this is obviously from this one, right? And you can see if you refuse fair bet, that's what you do in St. Peter's paradox, right? You're not going to pay infinity for that. That means that your utility must be a concave one. And that is, people said, in many cases, we make decision. That's why we buy insurance. Because insurance is losing, right, on expectation, right? Because you only pay more premium than your expected loss, right? That's how insurance company make money, right? Otherwise, insurance company is paying the expected value, right? By law of large number. Okay. So under Jensen inequality, that must be concave, right? Because that is the proof from the Jensen inequality that. So it is a little bit surprising because under expected utility, your marginal utility of wealth represent your risk, okay, which is completely unrelated to concept. Turn out to be under expected utility, that is, they're related, right? Say, if you're $1 million and give you $1 more, how much happy you are? Compare, suppose you have $10 million, give you $1 more, right? And you compare this additional $1 at different wealth level, right? And this actually with the risk, surprisingly. Okay? And this seemed to be the case that, right, as I said before, right, if you are looking at very small bets, you're more like risk neutral, right, compared to wealth, right? So this is surprisingly, two unrelated concepts they can link together. Okay, of course, whether it is true hinge on whether von Neumann-Morgenstern utility representation works or not. If not, then they are unrelated concepts. And of course, in more advanced model, they they are unrelated because people think they're unrelated, right? So that's why in a lot of macro model, they distinguish the two, right? Where your utility over the outcome should be distinguished from the risk preference. But in the standard model, they are closely related. They intertwine. You can't change one without changing the others. Okay, so this is maybe you can say drawback or the features of the classical model, but that's what you get. Okay, so that's what you see. If I give you $2, you have higher utility. I give you $2, I give you yield of 2, right? But bless you. So, but if you get you're choosing the random over 1 and 2, 1 and 3, you get much lower, right? So you would prefer to have U of 2 directly, rather than I ask you to randomize over 1 and 3, right? Randomize over 1 and 3 is just a midpoint of here, right? So any lottery over 1 and 3, right? I mean, half lottery, right? It's no better than, right? So you get any lottery, the expected value, okay, must be below than the 1. That gives you the certain outcome. Okay, so that's the. And the other one is with nothing. Okay. In the classical model, economists think that is crazy. No one risk nothing, or at least in business application. Okay, but of course, in recent days, and we know better because people go to casino, people buy lottery ticket. Right? Why? And one of the reasons is because we not only care about the mean and variance, right? We care about the kurtosis or skewness, this kind of stuff, right? You have a high, very skew, positive skew, right? You have a small probability of a high risk, high gain. You value that much. You value a lot, right? And later you see this as you overvalue the low probability event. Later you will see there's some kind of probability weighting can explain that. But in classical world, they think this is crazy. Okay? But nevertheless, we know this would fit this type of people. And that's called the risk loving. Okay? It's a convex thing because U of 2 is not as good as middle 1 and 3. Okay? So they want some excitement, right? So some people argue that because why? Because people enjoy gambling, the feeling of gambling. Okay, they want to play the heartbeat, right? 哇，那就是心跳, right? So that's what they care. Now we would define 2 terms called risk premium, which will be very useful concept. So if you pay the lottery, right? This is expected value. Okay. Risk premium will be the money that you like to pay to avoid the lottery, right? So if I give you the expected value, you like to pay this much to make sure that you have same utility of paying lottery. So how much you want to pay to avoid paying this game? Okay, this risk premium. Basically, you want to buy insurance, right? So if instead of this, right, I ask you to have this, right? And the other one is called certain equivalent, which means that this is the outcome. I give you this the same as you play the lottery. Okay, so that is equal to your wealth plus the value of the lottery minus the premium. But this is a little bit complicated. Let's see the graph. Assume you're concave, otherwise there's no point of talking premium. Okay. So again, it's like your lottery equal over 1 and 3. Okay. The expected value is 2, right? And if we're asking, okay, instead of paying the lottery, okay, which is average of this guy, right? I give you this much of money, CE, then you're indifferent playing lottery, or you just have CE, right? And in that case, this is a risk premium, right? Instead of getting on expectation $2, okay, you willing to pay this much. Okay, so this is the risk premium. Okay? Of course, why I did that? Why we care about this? The reason is we can't easily measure the U, right? But you can easily measure the C or the pi. Once you did that, that is a way to convert back to the U. That's why we want to measure risk premium. It's not because of we care about this, because it's only we observe. We can't observe U, right? Okay, what is your U? We can't ask you, what is your U? No one will tell you what they can't tell you. But you can give them, okay? Suppose you are 1 or 3 or lottery of this, or I give you any number that you avoid in lottery, right? I give you a fixed number. That's actually an experiment that's called the list method, right? You have a table, right? The option A is just a number amount, okay? You pick, and the other guy is like your lottery over 1 and 3, right? Then you tell me which number. This is your certain equivalent, right? I can calculate the risk premium. Okay, so this is actually this is how we done in experiment as well, to measure your risk preference. And once I have this, right, then I can fit this curve back and then figure out what's the utility function. Okay, so that's why we talk about this, right? Not because of we care about this directly, but this is how we do experiment. Okay, and you can also talk about the proportional risk, right? Instead of the risk, the lottery, just like proportional to your wealth, okay, is T minus 1 times W. And of course, if T is 1, then there's no gain or no loss, right? And expected value 1 is a fair bet. And in that case, you can write this is your certainty equivalent, right? Okay, this is expected value minus the premium. And that means that the relative premium is multiplied by the wealth is the absolute premium, or you can move the W down. Okay, so this is the proportional risk premium. Okay, so you can measure premium in 2 ways. One is absolutely, I give you the wealth, okay, right? This pi A depend on your wealth and depend on lottery, right? So it's characterized by the 2 things. Okay, same for the relative risk premium. Later we'll see why we would need that. Okay, why we will have the premium. Okay, and how to measure this premium. Okay, and we will decompose this premium into 2 parts. Turn out this premium, you see, consists of 2 parts. One part is subjective part, one part is objective part. Subjective part is how risky lottery. And the subjective part is how risk preference of individual, okay, which we will do immediately. Okay, so we will decompose this part, right? Because this is what we observe in the data, and how you can estimate that. So that's what we do. This risk premium is something you observe, right, from the experiment, right, from the real world. We will try to decompose it in 2 parts, right? Why? Because you ask agent different cases, right? And different cases will have different lottery, right? Given different lottery situation, you tell them to ask them to make decision, right? And you get this guy, right? And you control this guy, you can tease out this guy. Is that clear? Because premium actually consists of 2 things. What you observe is because you give different lottery situation to the agent, right? From very risky case and not so risky case, right? And you get many risk premium. We want to tease out the utility, right? So that's the idea. That's why we care about this decomposition. So variance by construction is the thing you learn in the undergrad, so I'm not going to talk about this, right? This variance. So Aeropress actually define this absolute risk premium. Not surprising result at all. So the fraction, the numerator is what we expect, concavity, right? The second derivative, right? Which how concave they are, right? And because of its concave function is negative, so that's why negative. The numerator is negative, this guy, right? The higher the number, the more concave you are, right? So that's nothing special. And you want to ask why I have to divide it by the first derivative, because remember utility is immune to off-white transformation, right? So that's why u of x or u of 2x is the same. So you want to differentiate that. In that way, then you are not, it's just normalization, right? So just want to compare across individual. So you just divide it, right? So basically just concavity, right? But you just compare, right? You can imagine this is what you learn in the undergrad in statistics. That is what the coefficient of variation, right? You normalize by the mean, right? Because this is just the mean, right? The location, the slope, right? The scale of your drawing. Now, this is the important proof. I don't spend the time to proof because this is very elementary anyway. If you want to really just Taylor series approximation, okay? I'm not going to do it. But turn out to be, if you're talking about fair bet, okay? Turn out very interestingly, your absolute risk premium is two part, product of two part. The first part is objective variance of your lottery. Okay? How various your lottery. The second part is absolute risk aversion. Okay? What does that mean? Right? You know many of this observation, right? Right? Because you observe how people make decisions, right? How many premium they want to pay. You make a lot of lottery, you decide the variance of the lottery, right? You make it further or smaller, and you can tease out this guy, right? So that is how you have risk premium in different situations can guide us what is absolute risk aversion. Okay? And once absolute aversion, then we're done, right? Because we know the second derivative, right? And then basically you can integrate back, get back our utility, right? Because you know how concave they are. So that is how you can get from risk premium back to our utility function, right? Okay, of course, once you know this, then you basically solving the partial differential, solving the differential equation, you get what we want, right? Because the first order derivative is decided by you, right? Because you can normalize. So u prime of, let's just go back here, right? You know this guy, right? And once you fix this guy, then you know this guy, right? This doesn't really matter anyway. Now there's a proof. I'm not going to go over the proof because that's a waste of time. So turn out that, if you look at finance or many investment literature, or that's most uncertainty is being used, or look at marketing or accounting, the CARA is commonly used, okay? And why this utility is being used? Because this actually gives you the absolute risk aversion. And why you want to do that? If you assume that, then the model becomes very simple, right? Right? Because the model, if you assume this F, you can calculate that, you differentiate that, it's a constant, right? That means that it's very simple to measure this. If this is a constant, right, you just run a regression, right? Right, then we're done. Right? You regress this over this is a constant, right? Then the slope is what we have, right? Just even when, if there's no reclamation issue, you can just run regression, then we are done already. Just one linear regression, right? Regress your risk premium over your variance of your lottery. The slope is our risk aversion, then we're done, right? We can easily estimate that, right? So that would be That would be the idea, right? That's why we care about that, right? And C is redundant anyway, right? And A just scaling, right? Then we are almost, we're just there, right? Right? Because A doesn't really matter, right? It's off-Fourier transform. C doesn't matter, right? So only matters B. Is that okay? So that is how you can estimate the thing. Okay. Now, you ask also, what about the relative risk aversion? Okay. And pet arrow have the same thing. You just define, because weighted by W, you have TW there. Okay. How do you define it? It's the same thing, but now the risk is TW, right? And for the fair bet T is 1, so that is, you put 1 over there. So that is the relative risk premium. And this guy is also related to the result, not surprisingly. The relative risk premium is just the variance times the relative risk coefficient. Right? Again, okay, if you have the left-hand side and you control the middle guy, then you're the right-hand side, right? So you can do regression simple. Okay? And very often, this is even more common to see this. Okay? It's called the constant relative risk aversion, right? So it's always constant. What does that mean? It means that your risk preference doesn't rely on the wealth, right? Suppose you have $10. I ask you to gamble for $1. Okay? This 10% of risk. If you have $1 million, I ask you a bet on 100,000. It's also 10% of the wealth, right? Then you have the same risk preference, same risk premium relatively. Okay? So this is, I think, more often than otherwise. The size, because we think that it's percentage of our wealth matter, not the absolute number. Okay? So your risk depends on the wealth, okay? Or your risk premium depends on wealth, percentage of wealth. You think about of the risk, you're not about absolute number, all right? But you're not talking, no matter, because absolute risk aversion means that the risk only depends on the absolute amount, right? No matter you have 1 million or 1 billion, right? $1 risk is $1 risk. Okay, doesn't really matter, right? Is that the? But if you have constant relative aversion, right? It's just like, for me, right? 1% of wealth. Okay, I need to take this amount of risk, same as Ma Yu, he take 1% of his wealth, right? Same idea there. And in that case, you will see the very common one, the log utility, right? So once you log, then everything becomes very simple, right? Or if you like, it's the AXB minus 1B. This is not common. Usually see this guy, right? This type. But the same transformation there, okay? Because just linear transformation. So this is the one you see very often because the B1 minus B cancel out, right? So that is, you see that very often. Okay. Why is the case? Because it really depends on, independent of your initial wealth, right? So it's just relative to your wealth only. Okay. Is that okay? Is that clear? So that makes our life much easier, right? Of course, if you assume unity, then you're locked, then you don't have anything to estimate anyway, right? But if you do that, then you still have something to estimate, right? Once you assume this is already, you know how people behave, right? Already. So is that okay? So that gives you the foundation why you often see this. Okay? So just to recap a little bit, that do remember in this course, right? We cover the utility case when you actually try to work is you may look at, in the case of certainty, you can look at substitute, right? Complement or coplocalus, right? Or even general case, you have the CES, right? It's the one that you look at when you have a complete information setting. And when you have incomplete information, right? We give you two example functions that have a good foundation, as you see all the time, is constant relative diversion, right? Or if you don't like this one, you think this doesn't fit very well, right? This is one that fit better, right? You think that people have constant risk, absolute risk aversion. This is what you think, okay? So this is the foundation for this too. But otherwise, you don't know why when you see in the literature, they come from nowhere, right? And they keep using this kind of family, right? And if you pick up any asset pricing textbook, they would spend 2 chapters to go over all this thing in, of course, much greater detail. But this is what you will see. And then they just, okay, from now on, we use Kara, right? And that is the reason, okay? Is that okay? I mean, of course, many of you have learned it in the undergrad, so it doesn't really don't have too much improvement, except that here we tell you, compared to undergrad, we tell you this approximation. The risk premium is related to the risk preference, and you can estimate that. So that's something that I don't think would cover in undergrad or master level, and this is something in the PhD thing we cover. So let me quickly finish this compare lottery. And here, there are many things when you compare lottery, but we'll give you 2 important terms that we have been using all the time when you go to a conference or when you read paper. Is what we call the FOSD and SOSD, which is the first order stochastic dominance and second order stochastic dominance. And so we have seen people can have very different risk preference, right? Can be risk nothing, can be risk neutral, can be risk averse. And the question would be, if I give you 2 lottery, A and B, can I compare them without specifying your risk preference? FOSD, first order, means that regardless of your preference, risk preference, as long as you like more money than less money, you prefer A over B. Okay? If A is FOSD, B means that regardless of risk preference, whether you're risk loving, risk neutral, risk averse, you like A over B. So it's a universal comparison. Of course, this kind of comparison will be incomplete, right? Many of the time you can't compare. But when you compare, it's very strong, right? If one is FOSD B, then you must take A. There's no need to worry about this. Of course, there are many cases you can't judge. That means that you have to get to the second one, because this one, you check it first, right? If A is better than B in FOSD sense, then you're done, right? You always take A, right? But what happens if you can't? Then go to the second order. What's second order? Second order means that I focus on the people who are normal, which means that they're risk averse. Okay? And I don't care about how risk averse you are. Okay? As long as risk averse, you always take A over B. And then it satisfies the second order stochastic dominance. Okay? So if you always take A over B whenever, no matter how risk averse you are, okay, then that is SOSD. Of course, it is often the case you can't compare the two, but when you can compare, then you're done. Okay, and why you care about this comparing different lottery without regarding risk preference? That's what you do when you look at, say, suppose you do financial planning, right? You tell them which option you're doing, right? If A over B in FOSD sense or SOD sense, then you just do A, right? And later you will see what it is. Okay, it's very simple. It's nothing new. It's not something complicated, but the name looks very complicated. So dominance is compare lottery for different type of risk attitude, right? You don't want to make a case, okay? Because if I know your risk attitude, then I can compare, right? Obviously, but I can't make the assumption, right? So the definition 1 is the fundamental definition. Okay? We said regardless for every possible U, right? That means that non-decreasing means that as long as you prefer more money than S, right? Then lottery F is better than lottery G whenever your expected value under F is better than G, right? So for every possible U, okay? And under what condition this is true, right? Regardless of whatever turn out to be, the only thing that this only holds true if and only if this F is less than G in terms of CDF. What does that mean? This thing looks crazy, but you can do the proof. I'm not doing any proof. You can check the textbook. What it means is like this. As long as F is below G, then that's the case. Why? Because F is below G means that the probability that the value is less than particular value under F is lower than the G. That means that probably higher is better under F than G, right? So F is better than G, no matter which point, right? For each possible point, F is below G, means that for every point, no matter what you look at, F earn more than G. So regardless of, as long as you like more money, F is better than G. Is that clear? Okay. Of course, you can prove it, but I'm not going to do any proof because I already said I already done one important proof, so I just skip. Okay, you can check. Is that okay? So you can easily see why. Because suppose F and G are the same, right? And then I give you $1 more for each cases, then F will be below G, right? So F and G originally the same. Okay. I consider F lottery. I give you $1 more for every scenario, then F will be below G, right? In terms of the CDF. Is that clear? Because you suppose I have a distribution, right? And F the same G, right? But I give $1, then we just like a shift a little bit, right? A shift, say suppose this. Give $1, then everything is a parallel shift. Right? So this just means that in this scenario, I'll give you a little bit more dollar. Right? But that's why it's always better, right? Just that's how you think, that's how I think about this, right? Right? If basically in this happen, then I actually have more money. Right? Every scenario I have more money than other way around. So as I said, the second one is I wanted to hold for any not just increasing, but I have another one is concave. So the important part is concave, okay, which is the risk averse. So if you don't take away this concave, then become FOSD. But when you're concave, then become SOSD. Okay. So it holds true for every concave function. Of course, turn out that I don't want to do the proof, but this is, I think this is done by Stiglitz, a Nobel Prize winner, and Lafont, they do it. What they show is if they have the same mean and the area you integrate from 0 to x is less than to 0 to g. So that's a little bit convoluted, but let's do the graph because this is not easy to see. So before we have is the G is always above F, then it's FOSD, right? But what happened in the cross? It's saying that you try to look at the area up to any point, okay? Go to any, you stop this graph at any point. look at the area under the curve up to that point. As long as the blue curve, the area under the blue is more than or equal to the red, then that's the case. Before it's always above, okay? Above is always area, is better, right? But now we're looking at the same, right? But not above, but as long as the area, okay? But remember, area is probability, right? The probability, right? So the probability that, yeah. So that is the idea, right? So that is the proof. I mean, it's very important. And of course, this is too tricky, right? Still, I mean, how can I solve this guy, right? I mean, I know how to draw a graph, but it's not easy to apply. So lucky that, I mean, look at the textbook. There's also equivalent result, okay, which we call mean preserving spread, okay? They're equivalent. Turn out to be, if you focus on a lottery, okay, X, okay, and you have a mean zero random variable epsilon, okay, and you take a Y, which as you add a random noise over there, there's a mean preferential spread. So FOSDG, okay, if G is a mean preserving spread of F. So basically the same thing, but you have more noise, okay? If you have more noise, then you don't like it, okay? So the same mean, basically, again, this is exactly the finance idea. Have same mean, but higher variance, you don't like it, right? So people look at risk and return, look at the stock, right? That both stock A and stock B, they have same mean. One has higher variance, the other one have lower variance, right? If you are risk averse, very simple, right? You just don't take the higher variance one, right? The same mean, right? So that's why exactly what you expect, right? So that's why it's very fit very well the mean variance idea, right? As long as you have concave utility, you only care about the mean and variance. Okay, but do note that we can't tell if they are different mean, right? And one have higher variance, one lower variance, we don't know. It's just saying that if they have same mean, you would always pick the one with lower variance. Okay? It didn't say anything about they have different mean, one have lower, higher variance, the trade-off, it doesn't say anything about trade-off. Okay? You only say is if you're risk averse, they have same mean, you pick the one with lower variance. Okay? That is the only thing it said. Okay? But of course, it do imply mean variance have something to say. Okay? Is that okay? We're not going to do the proof, but they're the same thing. But of course, this is very interesting proof. And you can see that's why you add the noises is SOSD. And that's why when you look at many models that have information, noises, they always call SOSD because that is what it means, right? You increase the noises, you add noise component, right? Because epsilon is a noise, right? You look at the market, right? With some noise, random noise, then that's become Y. So that's why we always said, what happens if you have the distribution is SOSD, right? It's very common you see this kind of statement, right? It's unrelated to what we're supposed to do, but this is, people use this kind of terminology, right? Mean preserving spread, right? Mean the same, but spread out more. Okay? Is that okay? Is that okay? So, I mean, it's more like terminology because you often see this SOSD and you can prove they are the same, right? So there's no need to worry about the problem. So after the break, I want to talk very quickly about some other application beside the Cara and the Cara. I don't know. Cara and the Cara, anyway. CARR, CRRA or CRRA. And I want to talk about two more things actually you will find in finance. One is called the contracted utility. Also, you actually in a lot of dynamic game or dynamic scenario, you assume people have contracted utility because things become very tractable. So you look at the operation management operation literature, they also consider this kind of utility. And I'll go to the one that you so often see in the finance literature. It's called the constant risk of absolute aversion and normal distribution. Okay, and this gives you very nice result. Of course, for those of you who interested in finance, you study this all the time. I just give you some case when the investor only care about mean and variance. That is the case. Either you have consolidated utility, or you have constant risk aversion with the risk coming from normal distribution. So that's why mean and variance will work. And also, of course, it does mean that when people would care more than mean and variance, why we care about kurtosis, why we care about skewness, must be breaking down of this assumption, right? Either you think the risk is not come from normal, or you think the risk is no longer the constant risk of aversion. Right? Of course, that paper try to relax those, okay? But that is not the concern, especially macro. Okay? They talk about macro finance problem, why the study about why stock market fluctuates so much than underlying economy, right? And that is something that being there. And I talk about some application, and then talk about some extension as well. So let's break of 15 minutes. We'll resume around the same time. Okay. So I'm not going to bother you with the you reply, so have fun. In case you have a question, just ask me. equivalence。所以佢哋做個幾年嘅公司叫做等於跟你玩 lottery 一樣。I give you this amount of money, you will be same as you're the same as you have this wealth. You pay this lottery value minus your dividend. Okay, so this bigger you and this smaller you. One side. Oh, sorry. This would be this is small u, small u. Sorry, this is one because small u is the standard. This is expected. Stand for the end of the bigger u stands for expected right hand side function. Yeah, this. But I reduce it. So what you say then? What is the same? So that's the same. The problem has side, and this has the drawer side on this horizontal line. It's the same. So if I ask you to, so the lottery is like over 1/2 is 3, 1/2 is 1, right? Yeah. If you pay this lottery, your utility is this guy. Yeah, you will give me this utility, right? This utility. But if I don't want to, you don't want to play this lottery, how much utility you get is this utility. Yeah. Then this is the amount. If I give you this amount, then you will be same as you pay the lottery. Right. So this is the risk premium, because this is how much you can pay the insurance company. If I'm an insurance company, I can collect this amount from you. Yeah. That is what it means. Okay. Okay. Right. It's this amount that it's an insurance company. I pay you. I insure for you. So this is after you take away the insurance premium. That is it. That's it. And the next question is stochastic dominance. It's quite counterintuitive. Which part? One or two? Like that. Like the first definition says that the regression of the left-hand side is the right. For every u. For every u, right. Given the f and g, this definition. So this is a definition. There's nothing to prove. So just saying that if f is equal to g, if there exists for every possible view, this is true. It may not be true, okay? But in many cases, it's not true. But if that's the case, then definition. And the key part is proving is this is equivalent to this.
That's why I feel because see in the later part, the equation inequality reverses direction.
Oh, because that means this is better, right?
Yeah.
That must mean that this F is the less than or equal to, right? It must mean that look at this number. This is below, F is below, means that more likely to have better outcome.
More likely to have better outcome. Why?
Well, because this is probability that is less than or equal to that when the CF, right?
Yeah.
So that means that F has more likely to have higher than G.
Well, the value is much
Because F is less than or equal to, right?
yeah.
So if F is bigger than value, right? So it's more likely to have lower value under G than F. So actually means G slightness. Right? So you take any value. This is area is G, right? And this value is F, right? So as long as this value is less than this value.
I see, because the probability measure sums to one.
Yeah,
so in the left tail.
Right. The left tail is smaller. This left tail is smaller. No matter where you look at it.
Achieves the allocation of the average probability.
No, it's okay. I just talk too much then.
Take a break.
Yeah, it's okay. Don't worry.
I will fix that. Because the allocation of the cross the CF sums to one. So if the L is less in this part, if it's more this one.
Yeah. But every part is allocated smaller. So
every
part is not every part
is better than G. Yeah. It looks quite counterintuitive at first sight, at first glance.
Yes.
But
But you can prove it, but I just keep the proof, right?
yeah, it glance by pattern.
Yeah. And you guys should have this graph in the future.
Thanks.
Because this is exactly to be small effort. Sorry. So this small effort.
Yes. That's all.
So let's continue. It's not too much left because what left is basically applying what we learned. So mean variance analysis. So as we said, in application, we only focus on mean and variance because this is the only way you can estimate many cases. And it will be, our model is simpler if we have a foundation to focus on mean and variance, right? So we don't care about the kurtosis, skewness, and so on and so forth, right? Why you can forget about those higher order moment? Two special case, as I said, the first one is you have constructed utility, right? So you can imagine this is Taylor series approximation up to second order. There's no third order, then you just care about mean and variance. And you also have other cases is constant absolute risk aversion, right? And then your lottery follow this one. Okay. So this is a proof, which I'm not going to do it. It's standard in the finance class. Okay. Of course, you care about the mean only variance. The proof is not complicated, but I'm not going to do it. Okay. And the second proof, second line is if you have constant risk aversion like this guy, okay, and your lottery actually follow the mean mu and variance sigma square, your utility only depend on initial wealth, your mu minus 1/2 of this guy. That's why when you often see asset pricing, they are maximizing this guy, mean minus the variance. So that is why, because it follow exponential utility. Okay, so that means that is mean variance minimizer, right? So this is, if you look at asset pricing, this is first thing you do, you minimize, of course. If you more add one asset, you have a covariance structure here, right? You minimize your mean and your variance, right? So this is very standard in asset pricing. And the proof like this, I'm not going to do it, but this generalized to multivariate normal, but I'm not going to do anything on that. You can check the proof for fun if you want, but don't care about this guy, as I said. But you can check the proof. I think you are Ph.D. admitted. You should be mature enough to look at this. But again, if you have a question, you can ask our TA to explain to you. Okay, the TA will hold tutorial right next week. Then if you have serious question over what I skipped, then you can just ask her to explain. I think that will be easiest because I want to spend some time on application. And this is something very simple, application of SOSD, right? You consider two identical stock have same mean, same variance, but zero covariance, right? And if you put all the money in one of the two, you get mu and sigma square. But if you split your money in alpha in one, the alpha in the other, one minus alpha in the other, you have same return, but your variance is lower, right? And the minimum variance is alpha is 1/2, right? And remember the same mean, right? So if you split, actually it's SOSD, right? Same mean, it's mean preference spread, right? So that means that regardless of your risk preference, I don't have to know risk preference, right? You always split, okay? So that's why don't put all the eggs in the same basket. Would work if you're risk averse, right? But if you're risk loving, you put all the egg in the same basket, right? Just reverse it, okay? So that regardless of your risk preference, right? So how risk averse you are, right? So diversification is always something you should achieve if you believe this theory, right? And there's also another model that tells you, maybe forget about this kind of commodity, maybe talk about risk insurance. Because this is the same as you saw there, saying that if you have no problem, you get the same wealth, but you have problem, you minus L, it's a loss, right? So
and the insurance company charging P dollar for premium, and then Q is your coverage. Okay, decide how much you want to insure. Okay, and then basically this become your payoff, right? If you don't have anything, then you just pay your premium, P times Q. If you have things happen, you minus L, but you plus bet the protection level Q, right? And that's why you maximize your utility based on your coverage. And turn out that how much insurance you would buy when you're risk averse is you buy full insurance if P is actually fair. Okay, but if you don't like this and turn out this is nothing new but marginal revenue equal to marginal cost, or the ratio of the two state of the world is same as the probability ratio. Okay, and I don't want to go into detail because this is undergrad level material. At the end of the day, if the insurance company, the premium is same as the pi, which is the fair insurance, then you would buy everything. Okay, so that is the main result. Okay, but of course, none of you are doing this kind of application, so I just quickly skip to this one because the proof is rather easy, because these are undergraduate material, so I'm not going to cover. Maybe I should put it in the, maybe I shouldn't use the red color, I should use the black color. So sorry, I should use the black color because this undergraduate material, I shouldn't put it as an example, but just telling you that, so you can safely, if you like, I will change all this application to black color. Not going to be, they are not examples, so it shouldn't be example. It's just example showing you that how you apply the ideal expectation, right? Expected utility into different kind of scenario. Okay, so I guess I shouldn't put red instead. I should have black. Okay, why I don't want to talk about this, because I want to talk about what is beyond the expected utility. I think I want to spend more time on that. Is first, there's two different things. First is it's no longer linear, and there are many different ways to be non-linear. First is it's linear in probability, okay? And psychologists think that the probability should be weighed differently, right? High probability is not going to be linear, maybe a non-linear curve, maybe a concave, maybe a convex, maybe any shape, and psychology use that. But the problem is when you have this type of model, it violates the stochastic dominance we have, which we think is very desirable. Okay? And that's one thing. The second thing is how to solve this problem is what we call the rank-dependent utility. Okay? And so far, when we look at your lottery, it is kind of satisfied independence. It doesn't really matter what is actually in the outcome. It doesn't really matter what the bundle you're facing. So rank-dependent utility, later you will see, it depends on what kind of decision you're making. It depends on the rank of the outcome. So it just, the option you have really matters. Okay? You can't really turn out to be related to the idea is how your probability change according to rank matter, which we will see very clearly. Okay? And that gives us one thing very important. It's called the prospect theory that often happen after 70 and 80 or 90. That is the Nobel Prize winning idea, right? Is people, when they make decision, it's not in terms of the terminal wealth, but rather in terms of win, loss, and gain compared to your current wealth. And people will win and lose differently, not the same. If that means that if you frame the problem as win compared to loss, they behave differently. So that means that if that's a famous experiment, ask people Suppose you have chance to save people, or suppose you have chance to kill people, they're different, right? Suppose there's a medicine, there's a way, right? There's the example like this. I think there's 600 people. If you have new medicine, you have the chance to save 400 people, right? Or if the medicine can kill 200 people, right? Depends on how you frame it, people behave differently. Okay, so that's very different in terms of you sell the thing to the medical doctor, right? Because they make the decision of living or dead, right? And turnover, interestingly, that is called loss aversion, and people are concave in the gain, as we said, right? Standard. But when lost, become convex. So become an S-shaped utility. It's like this. Your utility turn out to be, I don't know whether I have a slide. Your utility is like this. This is your X, okay? This is 0, and this is your utility, okay? What is your preference? Look like this. So gain a little bit is okay, but you gain a lot already, the marginality is very slow, right? And when you lost a bit, then you don't really like it. Even you lost a little bit, you're very sensitive to losing, okay? And you have to gain a lot in order to make you suffer a little bit, okay? Okay, so that would be the loss aversion. And later you will see the rent-dependent probability weighting there, also related to the prospect theory. And this application in finance, right, turn out to be this probability weighting is related to skewness, and in people actually looking for Google or Tesla, but I think in this case, a lot of people looking for OpenAI or kind of AI thing is looking at people making a lot of money, right? But anyway, let's see some example, okay? There's a free thing there. What is the standard one? Is what we have just covered in the beginning. It's called the expected utility, right? It's the, you look at each outcome, right? Certainty, you multiply by probability, that is the expected utility, right? And you can write in the following way, right? You can rank your outcome from highest to lowest, x1 to xn, like what we're doing. And we can look at the difference between the cumulative sum, okay, up to the before one, right? This is actually TI. Right? So while I do that, you will see very soon, okay? You can write the same way, okay? Now, the other way to think is you don't weight your outcome, rather you weight your probability, okay? And this is done by psychologists, okay? And I don't have time to show you. This type of model violates stochastic dominance. You can easily construct example. And that's why economists don't like it, because we think stochastic dominance is something that so obvious no one should violate. If violate is not a good model. Of course, that's why economists struggle for 30 to 40 years to figure that out now, okay? And this is the weighting, it's not linear. It's just like the outcome is linear, but your probability is not linear. As I told you, this model is popular in the 70s and 80s in psychology journal, but no longer people take it, okay? Not now what people take it is this guy, okay? It's called the, it's in the 80s, they discovered this rent-dependent model. It's closer to the prospect theory, but let's see what it is. This is saying that you still look at your outcome, U of X, right? Each outcome, look at it, and you summing all of that, okay? But you're not weighting by the probability. Rather, you look at the changes of this marginal probability, right? Look at this up to I compared to I minus 1. See, it's a marginal probability, okay? And you have nonlinear weighting over that. So that's why basically you add W over this one. Okay. Is that clear? What are we doing? Okay. So basically, just I should draw a picture, but so you can imagine like this. So you have x, right? Maybe this is x1, this is x2, up to xn, right? And you have some probability here, probability here, probability there, so on and so forth, right? So expected utility will be just the value x times probability, right? Just that is how the expected value works, right? But if weighted one, you just multiply, right? You either, okay, if you have expected utility, right? You just transform this u, right? This expected utility, right? Just transform this number to the u, right? Just go up, right? And the probability weighting is, instead of this, you transform this guy, right, to w. That is the PW. Okay. But rank dependent is what? Is what you will do is you look at like this, right? Because you ran from big to small, so you have x1 here, x2 here, up to xn, right? You have some probability. I don't know how it looks like. Okay. Okay. And what you're going to do, okay, is look at each outcome. Suppose this is xi. Okay. Instead of looking at this probability, right, multiply utility of this guy. What you're doing is you still have utility of this guy, but look at a value, okay, or this guy, okay, minus or this guy. Okay. Is the orange one, you transform to W, minus the green one, you transform to W. Okay? If you look at the probability weighting, you just transform the red guy. Now, instead of the red guy, just all the way from above, and green one. It's the marginal changes, not, it's a utility over the sum of the probability. Okay? You're looking at the probability more than or equal to that number compared to the other case, the marginal difference. So that's why I said in the beginning slide, it's like log utility is not the overall utility matter, but the marginal utility matters. And that's a classical case of diamond and water paradox, right? And the utility of water is very high, right, compared to diamond. But the marginal utility of an extra unit of water is lower than the extra unit of diamond, right? So that's the same idea here. Just additionally, okay, how this probability changes. Okay. So once of this, you can easily see how prospect theory works. It's simply you divide things into gain and loss, the same function. Prospect theory just like gain and loss are different things. You have different way to weight the probability because one is concave, one is convex. Okay, is that okay? So something like this, but you will be, if you use it, you will know, right? Only often you will see this in the finance theory, because this is something people think this is more appropriate to model finance situation. Okay. But of course, I think many of time you will be doing is just like the Cara and normal, that's something you would do. But if you really do something serious, this is the prospect theory, because I hope I introduce it to you. Then when you read the papers, then you will not be surprised people talk about prospect theory. It's nothing very deep, right? Because just same as expected utility, but the probability is not linear. Okay, and the reason why you have to do this complicated thing is because, as I said, if you just do this kind of transformation, doesn't satisfy stochastic dominance. Okay, so what we're going to do is you have to order them from the top to bottom. Okay, you look at the survival function, the difference, and that is the only way you can have a consistent model. Okay, so that's the reason. I don't know if they like it, but this is only mathematical. That's why economists actually spend a lot of time to figure this out, right? It's not something like they just do it quickly. They have to actually spend 30 to 40 years to come to the ultimate prospect theory you see, right? And this one is not the best, but this fit very well in a lot of experiment, and it's still used in a lot of application as well. Okay. And something beyond uncertainty, as I said, beyond risk, right? And there's some uncertainty, right? So if the probability is not objectively known, right, then how can we make decision, right? The idea is the following. Standard is like, I, right, have a box of balls, or red or blue. You don't know the number, right? If you know the number, then it'll be a risk situation. If I don't tell you which one, right, then you're guessing what's probably there, right? You make decision, right? So that would, you have to make some idea how to do, right? So that's why it means that you have to figure that out. What are you going to do? Okay, let me say it this way. Okay, so this choice under uncertainty is following. So that you will use different types of terminology because they're very different. So you have to, instead of talking about different outcome, you're talking about state space. There's a state of the world. Okay, and this is very similar to what you see in the modern probability model. You have events, right? Some subset of sample space, and then outcome with the amount you get. Okay. And prospect, it is saying that you, from each state of the world, you map to some outcome. Okay. And you consider this as prospect is the way you take action, right? You do, suppose you have umbrella, right? It depends on whether sunshine or not, right? If sunshine, you get payoff of 10. If there rain, you get payoff 100, right? And the prospect is just the action you're going to take, okay? And there's no probability. Looked at, there's no probability because it's decided by you, okay? And you would be a prospect. It's just like in different state of the world, S1, that's what you earn, okay? But you don't know the probability of S1 or S2. It's subjectively by you, okay? So there's no subjective probability. You can imagine S1 is it rains. S2 is sunny, okay? And one prospect, X, is like you take the umbrella, right? You take umbrella, then maybe it rains, you get $500. If it doesn't rain, you get $2, right? Another prospect is you don't take the umbrella, right? You just go hands-free, right? And if it's sunny, then you get a lot of payoff. If rainy, then you get very negative, right? So this is called the action. And people have preference over prospect, right? Because I can't have a probability over. I have subjectively, right? But there's no objective probability to rain or not, right? But you still choose some action, right? Every day, right? You decide whether to bring umbrella or not, right? But I observe your action. I try to infer two things. One is I infer your utility over outcomes, and I also infer your probability, right? So the question is, I saw what you're doing, can I infer your probability? Okay, it's one more step, right? I've joined it as a joint problem. I want to know your probability of each state of the world. I need to have to know what utility you get from each state of the world, right? So it's like way more complicated, right? It's two things, right? Before I had the probability, the only thing I need to worry about is just utility over the outcome, right? But now is I have two things. I have to know how you assign probability of that, right? But I only observe one thing, how you choose, which one you choose, right? Whether you take umbrella or not umbrella, right? And in that case, okay, turn out, okay, very interestingly, you can still have expected value, okay? Just as your, very simple, right? If you only is risk neutral, right? Then you have expected values, only you care, right? And there's a salvage, have a subjective expected utility, same expected utility, but your P depends on what you think, what's likely. So it depends on people's think about the likelihood. And more recent papers, they use a model called Fouquet integral. It's kind of related to a complicated integration method. It's related to somewhat fuzzy logic, if you know what it is, but I don't want to bother with that. You can check those papers, but they are way, because when you look at papers, they talk about a lot of prospect theory, they talk about a lot of subjective probability. You don't know what it is, but what it is subjective probability is like, based on your preference, you can induce how people think about the probability. Okay, but I think we didn't give you good example right now. But the example like this, okay? You have some event over there, okay? So you will be able to say subjective utility. It's just like people will have subjective, you have a P function that are assigned each event what it is, okay? So that means that, as example, I have an umbrella, rain, and sunshine, okay? I saw you bring umbrella, right? And then I would say you would assign probability what to the sunshine and what to the rainfall. If I ask you many questions, I'm able to get that. I'm able to get a probability. Not just one question. I have to ask a lot of questions. I can elicit your probability. Okay. And also, I would also have the same thing, right? But now the probability all become subjective. Okay. And this is also why you care about all this, because in many cases I don't have probability. Right? Suppose I look at an investor invest something, right? Can I say the probability going up have certain percentage, going down something? I don't. Right? In many cases, actually, we are doing this subjective probability, right? Investor has some idea how likely the stock will go up, how likely the stock will go down, right? Depends on what he thinks about the future. Right? So how do we do that? We are trying to say, okay, as long as it satisfies some axiom, which we don't have time to go over, then you will get something very familiar. Of course, in order to recover this, then you have to ask way more questions. But at least we'll say, even though things don't have subjective probability, objective probability, everything will go very nicely as well. So there's no worry about writing a model. Even the probability is not known by you as a observer. He has consistent probability system in his head, right? Although I can't see the P, right? In the standard case, right? I have to know the lottery, I know the P, right? But now he said even the probability is in his head, right? As long as he's not crazy, right? There's some system there, it still works. Okay? So just solve the problem of when you don't have the probability, right? As long as he thinks there's a probability over there, things are all right. Okay? And you can also guess, you can also take it out of that, but I don't think I have time, but that was the idea, okay? The VNM is looking at the pure risk, and salvage look at the pure uncertainty. Of course, we can combine those, and if you want, you can read all this paper. Of course, I would warn you, they become so sophisticated. It's very time-consuming to read those, but if you are time constrained, I would recommend you to read one book that is very easy to read. Okay, I recommend this book. I think this book. Let me see. Yeah, this is the book. Wait, is it this book? Yeah, or you can. Oh, okay. Maybe you can read this. I mean, this fee. I mean, it's good to read. I mean, this fee is good to read if you really want to update yourself to the recent literature. Especially you can see the title already, right? People actually looking at non-expected utility theory. Okay? And yeah, I think this should be this book. I mean, this is the book that is simplest enough you can read without too much problem. Okay? So I shouldn't spend more time than we do. And then we are done with the uncertainty. So probably next week after the assignment is over, I mean, they will give you another assignment for the uncertainty. Okay. So I will see you. I will stay around to answer the question you may have.